Hi everyone, my name is Yedutun Pahabol, with NIM 2510110300024 from Math Class B. Here I will discuss the mathematical logic in computers. 1. Introduction and levels of abstraction. Have you ever wondered how a machine made of metal and silicon can think? The answer isn't magic. It's logic. Behind the colorful interfaces, computers operate at a very primal level, the binary system. In the binary world, there are only two states, 1 on/true and 0 off/false. Computer logic is the set of rules that govern how these 1 second and 0 seconds interact to make decisions. Think of a light switch. It can only be on or off. However, if you combine millions of these switches using specific rules, you can build a digital brain. 2. Logic gates, the building blocks. The smallest unit of information processing is called a logic gate. There are 3 basic gates we must understand. AND gate, it will only output 1 if all its inputs are 1. It's like a promise, I will go if it is sunny and I have money. If either condition isn't met, the result is 0. OR gate, it will output 1 if at least one of the inputs is 1. I will be happy if I eat pizza or a burger. NOT gate, this is an inverter. If the input is 1, the output is 0, and vice versa. By combining these 3, we get derived gates like NAND, NOR, and XOR. The XOR exclusive OR gate is crucial because it only outputs 1 if the inputs are different. This is the foundation of arithmetic operations in computers. 3. From gates to arithmetic, the adder. How do these logic gates perform math? Let's look at the half adder. By combining one XOR gate and one AND gate, we can add 2 binary digits. The XOR is used for the sum, while the AND is used for the carry if the result exceeds a single digit's capacity. When we combine thousands of these circuits, we form the ALU arithmetic logic unit. The ALU is the heart of the CPU, performing all the calculations and logical comparisons that allow you to run apps or play games. Logic in programming in the future. Logic doesn't stop at hardware. In programming, we use if-else statements. This is a high-level representation of those same logic gates. If a condition is met, do A. Otherwise, do B. Before physical logic gates were ever built, a mathematician named George Boole formulated a mathematical system called Boolean algebra. This is the mother tongue of all computers. In standard algebra, we deal with infinite numbers, but in Boolean algebra, variables have only 2 values, true or false. Why does this matter? Because through Boolean equations like $b equals y for AND or $+ b equals y for OR, engineers can simplify incredibly complex circuits into more efficient designs. Without this logical simplification, your smartphone processor might be the size of a house. Logic also governs how data moves. In the von Neumann architecture, the logic unit, ALU, doesn't work alone. It collaborates with the control unit. The control unit acts like an orchestral conductor. It uses logic to decide which instructions to fetch from memory, when to calculate, and when to store the results back into RAM. Without this control logic, a computer would just be a pile of calculators with no idea what to do next. Every click of your mouse triggers millions of branching logic operations that determine the entire workflow of the operating system. In conclusion, every pixel on your screen and every line of code you write is the result of millions of logical decisions happening in a fraction of a second. Understanding computer logic isn't just about technicalities. It's about understanding the fundamental language of our digital age.